So we developed an automatic test system for a medical device by using a camera to capture an image and process it through our computer and control the product to push a button.
Videos can be done.
Okay, let's go.
30 seconds. Here we go.
Capture the image, we segment out the buttons, and then we pick which buttons we want to pick.
OCR does recognition, verifies it's right, captures screen, does it again. Start interrogation, boom.
Programming a medical device. It's that easy way to put it.
Our project is a desktop mini Segway that will be used for System 1 labs. It is to teach students how to build control systems for an inverted pendulum. They would use Simulink to build the model and to simulate it to the appropriate gains, and then from that simulation they would put it into reality and put it into their system. And they would build this little mini Segway to do the testing.
So
And then the final result would be
actual
it balancing itself.
So what the students want to do, they'll make their own weapon, and then they'll be able to they have super special AI that they so it supports the
This is the Mercury Robotic Competition. This robot here has to overcome a lot of obstacles. It has to, be controlled from over 50 miles away. It has to accomplish a speed test. It has to be able to pick up and deliver a beanbag and launch it 6 feet. Okay, so we have this one, Omega.
Alright, we're the Mage 2 project. It's a platform designed for to let the Senior Design 1 students develop weapons for their projects so they can get more hands-on experience with designing products. The design of this is to be totally wireless, unlike the Mage 1.0 system, so that it can fulfill the goals of being both mobile and active. With this, we have our server, which is what you see on the display right now. It's designed in the Unity game engine to actually look like a game. So you can have all kinds of effects and damage types and heal types, that kind of thing. There's 2 hardware components, which you see CJ and Sean and Patrick over here with. There's the player interface unit, which is this device. It has a heads-up display, which shows the current health status of the player. It also gets overwritten to show what direction you're being hit from, and that kind of thing. It also has haptic feedback motors on either side, which give some feel feedback to the system if you get hit. It has IR receive on all 4 sides, so that you can be hit from any direction, so the game can truly be all over the place.
We are the Megahertz Gauss meter team, and our design objective is to create a device that can measure an alternating magnetic field from the magnetic field generator in a large bandwidth. And so what I'm going to do right now is that this is resonating at 540 kilohertz. And we should pick that up if I change these buttons. Go from that range. And so right now we're picking up the frequency of this magnetic field and the amplitude voltage as well.
Magnetic fields are invisible, and so to prove that the alternating magnetic field generator is actually producing a field, I built a coil, and this coil powers lights. So when it's in the field, the lights turn on. When it's out of the field, the lights are not on.
Alright, we are the Neuron Emulator Group. Our job was to recreate
a neuron. What a neuron does is it receives an input signal, and when that input signal exceeds the threshold voltage, it fires a pulse. So as you can see in our beautiful demonstration, about every 4 seconds a pulse is fired because the threshold voltage has been exceeded.